Thank you, Inhi and Sengwu, and thank you all for coming. So, am I audible at the back? Okay, great. So today I'm going to talk about how do we combine the household travel survey data and the smart card data to generate the spatiotemporally heterogeneous activity schedules for transit riders, right? So it's a very challenging and new area because new data sets are coming. How do we utilize the different data sets to do the better activity-based modeling, right? So this is under the theme of how do we do the better activity-based modeling by utilizing the very different data sets that are available. So I'll first set up the problem that what we really want to achieve. So if you think about the activity schedules, what we have is 4 type of attributes. One is the X, which include the age, gender, income, and all sorts of sociodemographic activities, right? Y is I'm defining all the travel mode, trip purpose, as well as the number of trip sequences that we have in the activity-based, in the activity schedule. The third part is the S, which is the spatial attributes, like sequence of the spatial stamps in the activity locations. And time is the time stamps of each activity schedule. So in principle, if you think about this problem, if you generally we discretize the age, gender, and income into the categories. And we do the same for the trip purpose as well as the travel modes. So we kind of have a very large joint distribution that we want to estimate. So if we assume that the X is a discrete random variable, Y is also discrete, S is also discrete, T is also discrete, we have a large space of domain of the billions of attribute combinations that we really want to actually understand the probability mass on the each attribute combination, right? That's what we will have, and then we will have the activity schedule, right? The distribution of the activity schedule. So I will be using X, Y, S, and T a lot. So just remember this notation as we move forward in the presentation. Let's try to understand that when we try to generate the activity schedule using the traditional household travel survey data, what are the problems we face? So what we do is we take a very simple example first. Let's say we have only 3 zones, right? A, B, and C. And let's look at the number of trips, home to work trips, from zone A, B, C to other zones A, B, C, right? These are commute trips basically, right? So if you look at the commute trips in the HTS data, even if your population is, let's say, 5,400, you can take any number. I just took the 5,400 for some future convenience calculations. We generally observe the very small sample out of this population, right? So let's say your household travel survey data sample has just 20 respondents, but your population has 5,400 citizens or travelers. When you look at your household travel survey data origin destination matrix, maybe it may look like something that you observe here. But when you partition this matrix further into with respect to the departure time, let's say you split the whole matrix into the 2 timestamps, which is departure time before 9 a.m. and departure time after 9 a.m., you will start seeing a lot of zeros in the cells because household travel survey data sets matches the marginal distribution of the demographics with the true population. It doesn't match the spatial or the temporal distribution what you observe in the population. It's impossible to do that because even matching the marginal distribution of the demographics is very difficult in the HTS data. So the point is, and similarly in the population, you see these cells are not zero. There are observations, like from zone C to zone B, there are 200 people going in the population, but in the survey data, you might not observe any of those people, right? So let's say if you don't do any probabilistic thing, but you just want to extrapolate these matrices to generate the population. If you just extrapolate these matrices, your population will not have any trip from point C to point B because your sample doesn't have any trips from point C to point B. That's when we do the deterministic modeling. And this problem even becomes worse if you start splitting and add the more variables, more attributes to the data, right? So if you have the gender as well, then you will see the zero cell problem will become worse. So what we are trying to say is your household travel survey data has a very low spatial information, and that's a problem because you have lot of missing information about people going from one zone to another zone. The one possible way to address this problem that we do these days is we use the discrete choice models, right? That's a traditional way. We try to do some probabilistic modeling. So let's say this is our joint distribution, x, y, s, and t. What we can do is we can break into the two distributions conditional on the x and yi. And we generally try to estimate this location and the departure time choice problem. So we try to make it probabilistically, learn the distributions from where we observe the trips and try to infer where we don't observe, basically. It partially addresses the zero cell problem because you can generate some trips at the locations where there is no trip. But we know that it is very difficult to do the destination choice using discrete choice models because the choice set is very large. Number of spatial locations are a lot. And also, when you are doing in the steps, like you're doing first the spatial location choice, then the temporal location choice, what you're doing, you're missing the connections between the spatial and the temporal dependence, as well as the dependence between the demographics and the other attributes. So you lose the dependence, and at the same time, you suffer from the problem of the curse of dimensionality because of the number of choices. So it's a challenging problem. So what I want to establish here is that HTS data has the low spatiotemporal heterogeneity, and that makes things difficult to model the spatial and the temporal dimension. The second part, which we haven't focused yet, but the low frequency of data collection. We collect after 1 year, 4 years. These days, after COVID, people have started collecting every 1 year as well. At least Singapore started doing that. But generally, it takes like 3 years, 4 years, we collect the data. So it's a low frequency in that sense. So that's a data limitation. When you think about the econometric modeling limitation, it's very difficult to estimate the destination choice model. At least I'm not aware of a very good destination choice model that can be estimated. And there is a lot of inconsistency happens across the choice dimensions when you try to model the one dimension of the activity at a time. Okay? So it's not a very good idea to model one dimension of activity and just zipping them together later on. So what we are arguing that there are data problems and there are model problems, right? Both problems are there. But we have some new data sets that may address the data problem, but we need to come up with new methods as well to then utilize the benefits of these new data sets. So one data which we already have, because we are talking about the activity schedules of transit riders, then one thing which is very useful is smart card data, right? So I'm using the Seoul data. So you might be familiar a bit with the context that I'm going to talk about, because Eugene Kim from Aju and Hugh Chung is also involved in this research. So that's how I have access to this data from smart card. So if you look at the spatial distribution of the OD pairs in HTS, household travel survey data, this is the HTS that I will be using. SC is the smart card data. I will be using throughout SC for the smart card data. If you look at the spatial distribution of the HTS data and the SC data, you can see that the number of OD pairs that you observe in the SC data is much higher compared to what we observe in the HTS data. This is just another validation of the example that we have done. Okay? So I think you have around 400 something zones, so you can have maximum 160,000 some pairs. You observe around 138,000 pairs in the SC data. In the HTS data, you only observe 30,000 pairs. So you don't even observe the trips in the remaining 90,000 pairs in the HTS data. So you can see how severe the zero cell problem is that we discussed in the HTS data. So if you think about, okay, we are convinced that the smart card data has some important information, but what are the challenges if we really want to combine the smart card data with the household travel survey data? So let's try to understand that. So if we think about the household travel survey data, we have the resolution at the DZP zone level, and we have a, we have a temporal resolution. That's not a big problem. The main problem is about the sociodemographics part. we don't observe the sociodemographics in the smart card data, right? And the other problem is we only observe the transit tours. We don't observe anything out of transit activity, right? So two main problems. There is a mismatch in the information that we have in the smart card data and household travel survey data. And second is we don't have the non-transit trips in the smart card data. So how do you bring the joint distribution? How do we take the distribution from the smart card data of the only transit trips and use that to create the more spatially heterogeneous distribution using HTS data more elegantly as well? That has some interesting properties that we are going to talk about. So I hope the problem is clear and what we are trying to solve is clear, but let's formally define what we really want to achieve in the end. So we want to combine the HTS data with the with the SC data to create the joint distribution of all the four type of attributes that I mentioned. Just to remind, X is demographics, Y is travel mode, trip purpose, and the number of trips in the activity schedule. S is the spatial stamps, and T is the temporal stamps of the activity schedule. Okay, so we want to learn the joint distribution, and we want to combine the information from the HTS and SC data, right? But what do we want to do when we try to merge these distributions? We know that the X and Y variables are well observed in the HTS data. The distribution is very well observed in the HTS data. So we want to have a very good representation. The joint distribution should have a good representation of the HTS data in the X and Y. But when we comes to the SC data, we want to maintain the spatial and the temporal of the transit trips at least. That distribution we want to maintain in this fused distribution, right? So this is the part which is difficult to do if you use any deep learning or any type of generative modeling, whatever you do. Ensuring this is very challenging. So we are doing a separate study using traditional data-driven methods. But what I'm going to present is more analytical way of doing this data fusion. But we are doing the more separate one where we cannot guarantee these things. But here what I will show is the formulation where we can guarantee that we match in the fused distribution. We are presenting X and Y more from HTS data, which is similar to HTS data, and S and T, which is similar to what we observed in the SC data. Okay? So this is our problem statement. Just to put it from the example perspective, what we observe in the HTS data is, let's say, demographics, space and time, departure distributions. In the smart card data, we don't observe any demographics, but we observe the departure time distributions and only for transit trips. And our objective is to actually generate the joint distribution by utilizing this information. Broadly speaking, assuming we don't have any non-transit trips, this is what we want. We also have the issue of the non-transit trips that we will address shortly. Okay. Okay, so let's think about this data fusion problem from a basic principles that we have learned so far. So what do we want to do? We want to find the joint distribution of the X, Y, S, and T, right? And what we want to really minimize is we want to minimize the distribution of X, Y, S, and T that we observed in the HTS. We want to minimize the distance between these two distributions, fused distribution in the HTS data. But at the same time, we want to also maintain that whatever is the S and T that we are observing in the fused data, that distribution should match with the smart card data, because that's the constraint that we want to maintain. This is the better distribution that we observe from the smart card data. And if you think about this joint distribution, it's like we want to find the probability mass function for each of the attribute combinations, right? So if you multiply the X, Y, S, and T, you will have actually billions of feasible combination, because S is the spatial dimension, T is the temporal dimension, and X has many demographic attribute categories, and Y also has trip purpose and the travel modes and the number of trips. So ideally, this is what the problem look like, that we want to minimize the distance between the fused distribution and the joint distribution while maintaining the distribution that we observe in the SC data, right? And this is just nothing but that probability mass sums to 1 across all the points that we have in the space, right? And this is just, again, the probability mass should be greater than or equal to 0 for at any point, right? But this seems like a good way to define the problem, but it's just too many variables. It's just difficult to solve this problem as it is, right? Just to reiterate the point that here S and T include all the timestamps and the spatial stamps of the activity schedule. We haven't distinguished the S and T that we observe in the transit data yet. So we don't observe the S and T, full S and T in the smart card data. We only observe the S and T for the transit trips, right? So as of now, we cannot directly work with this formulation, right? Because what we observe in the smart card data, if this is a whole trip by a transit rider, what we observe is only this part of the trip in the smart card data, which is location x1, location x2, and the timestamps. This is what only we observe in the transit data. So we don't observe all the S and all the T's, we don't observe all the X's, right? We only observe this information from the transit data, right? So what we can do is we can actually define the problem in terms of the S bar and the T bar, okay? So S and T, just to remind, S and T are all the stamps of the activity schedule for the space and time, but S bar and T bar is what we observe in the only smart card data, okay? So just to distinguish the S and T, S bar and T bar is for transit trips, S and T for all trips in the activity schedule, okay? So because we don't observe the S and T for the whole trip, what we can do is we can split this problem into the data fusion and the inference problem. So the idea is as follows. So what we do is, rather than learning the joint distribution of the x, y, s, and t, we learn the joint distribution of x, y, s bar, and t bar, okay? This is the data fusion part, which is like the same problem that we have seen in the beginning, but with the S bar and T bar. It's not the S or T. But conditional on the S bar and T bar, and actually Yj, you can put the X here, we can then learn the distribution of the out of transit activities, space and time locations, right? So this part that you have here is an analytical part, right? This is an analytical part that we will be solving. But conditional on you have done this data fusion, you have now the good distribution of x, y, s bar, and t bar, then you can use the distributions from the household travel survey data to populate the non-transit trips, space, and the time. So to make it more clear, what we are doing is, let's try to understand the steps that what we are doing in this whole process. So just to remind, what we have is the Y has the maximum sequence trip purpose of each trip and the travel mode, and S bar T bar is the transit space and time stamp. Step 1 is actually the data fusion step, which is this part, knowing the joint distribution of X, Y, S and T bar, S bar and T bar. So if you look at the step 1, after step 1, how the output will look like. So you will have the joint distribution of X, Y, S bar, and T bar. That means, let's say this is a transit trip, you will have the departure time and here, but you will not know the timestamps of the non-transit trips. At the same time, what you will not have the locations of the non-transit trips, but you will have all the information about the Y, S bar, and T bar. So good thing here is that when we are fusing only the transit trip data from the SC, and the X, Y, and S bar T bar data from the HTS data, we have actually got the good pivot points from the transit trip data. And we have a very rich distribution that we transferred from the smart card data to the household travel survey data. Now the remaining task which is left in the step 2 and 3 is to get the space and the time stamps for the non-transit trips. So what you can do for the space and time stamps for the non-transit trips is you can try to find the distribution from the HTS data, conditional on the y, s bar, and t bar, and use those distributions to simulate the space and time stamps, right? So this part, y, s, t bar, finding the y, s, t bar and y, s, t, these two parts are very straightforward in the sense that you learn the distribution from the HTS data, conditional on y, s bar, and t bar, and you just transfer that. The part which is challenging and is the really combining the finding the joint distribution of x by s bar and t bar. So this part is traditionally, this is how this is done once you have the some information in the HTS data and you have to transfer. But the most challenging part is the first one. So I will be focusing on the first part, that how do we do this data fusion for the transit trips and the x, y, and s and t information that we have in the HTS data. So now we will focus on the first part of the problem, which is this part of the problem. This part is fairly straightforward because you can learn this distribution from the HTS data and you can transfer that very easily to the data fusion problem. So if we look at the data fusion problem now, because now we are dealing with s bar and t bar, we are no longer dealing with the s and t. So you can see that you have everything is replaced by s bar and t bar here instead of s and t. This problem is same as what you have seen in the beginning. The only thing which is replaced is s bar and t bar here. But again, the problem is of the too many decision variables has not been solved yet. Okay. So the one way to handle this problem is, what you can do is you can go about a clustering, right? You can just try to find some clusters where you can transfer the information between the HTS data and the smart card data to handle this this problem. So how do we go about that is as follows. So what do we do is, using the s bar and t bar, we create the clusters, k clusters, okay? But that's what I'm going to talk about, that it's not a trivial clustering. And what are the things that we need to be careful when we do this clustering here. So to simplify this problem, to reduce the dimensionality, at the same time to get the household travel survey data and the smart card data at the same resolution, because once you create a same resolution, there is a way to transfer information between them. We use the s bar and t bar to create the k clusters, and this data fusion problem approximates at the cluster level. Okay. So what happens now, the next part which is more important is, once this problem is simplified at a cluster level, what we can do is, we do some probabilistic manipulations, gymnastics with it, and we make it little bit simplistic. So the problem that you see here, it can be exactly solved by solving the much simpler problem. So why is difficult to argue, because answer without going through all the math, but I'll give you the intuition that why it is a simple problem to solve. But we prove in our work that this problem is equivalent to the solving the previous problem. So let's understand what exactly this problem is and how we are solving it. So now our problem was finding the joint distribution of x, y, s bar, and t bar, and we can write it as a xi, yj, ck fuse, and these two distributions which directly come from the SC data. Now the thing is, this fuse distribution xi, yj, ck fuse, what we are doing is, we are minimizing the distance between xi, yj, ck fuse and what we are observing in the HTS data, and then we have this constraint that this marginal distribution should be equal to what we are observing for the probability of each cluster in the SC data. The good thing about splitting this problem in this way is, earlier we were solving I cross j cross k problems. Here what we are doing is, we are solving this part of an optimization problem for each cluster. So now for each cluster, what we are finding is, we are finding the probability mass of the x and y for each cluster. I will give you an example just to make it clear that what this expression really means and what these probabilities really means. But the point is, once you break it up in this way, then you are not solving the optimization problem with I cross j cross k decision variables, but OK subproblems, which is case-up problems with I cross j decision variables. So for this, how do we go from here to here? There is a lot of math involved, so that we can look in the paper. But this is mainly the problem that one need to solve. So we need to understand that what we are gaining by actually doing this optimization. Why can't we just change this xi, yj, ck fuse with the HTS data, right? We can also think about it, right? Why are we solving this optimization problem? The point is, if you don't solve this optimization problem, you cannot maintain the joint distribution of the S bar and T bar that you have in the SC data. This optimization problem helps you in maintaining the S bar and T bar distribution in the SC data when you do create a fuse distribution, while maintaining the minimum distance between the xi, yj in the HTS data with the fuse distribution, okay? So I'll show you through an example that if you don't do an optimization and you just replace this with the HTS data, then what will happen, okay? So let's go. So just to put this framework in perspective, you get the S bar and T bar, the spatiotemporal attribute of the transit trips from the HTS data, spatiotemporal attributes of the transit trips from the smart card data, and you use the spatial clustering to get them at the same level to transfer the information. And then you can see that you reduce the you minimize the distance between the fuse distribution of the xi, yj, and ck, conditional on maintaining the distribution of the PCK-SC, right? This is the constraint, if we remember. And once you have this xi, yj, ck fuse, then, and you have the S bar, T bar, ck, you can use both of them to create this joint distribution. This is nothing but corresponding to this equation, the last part. And the constraint is this one. So this is the constraint that you can see, and this part is basically the first equation, okay? Now, one property that I was talking about, that why this optimization is important, it helps us in going closer to the x and yj that we observed in HTS data, while maintaining that the S bar, T bar that we are observing in the SC data are maintained in the fuse distribution. So the property that we can derive, if we can create clusters in a way that the probability of the cluster in the smart card data and the HTS data is same, then PXY fused is equal to PXY HTS, okay? So we will fully maintain the distribution in the fused data if we can maintain this condition. We can show this analytically, and I'll tell you the implications of this. And because we are solving this optimization problem, we always maintain that the fuse distribution is of the S bar, T bar is same as what we observe in the SC data, okay? So now let's look at the example and try to understand, okay, one more thing before we look at an example. So that means that we want to solve the optimization problem. We are always trying to bring the XY HTS close to what we observe in what we get in the fuse data and S bar, T bar in the SC data. So using this proposition, what we are trying to do is we can create the clusters in a way that we minimize the distance between the PCK HTS and PCK SC, because that will help us in getting closer to the X and Y distribution that we are observing in the HTS data. But while doing that, we also need to ensure that we don't have the many clusters where there is no observation in the HTS data. Because if you start creating the clusters where you have no observations within the HTS data, in the HTS data, then you will again get into the same zero cell problem, because there will be no information transfer happening. So let's take two extreme examples. One is you have as many clusters as the smart card data points, right? If you have as many clusters as you have smart card data points, then you have as many zero cells as you have in the original data, because you will not have the enough observations in the household travel survey data. The second extreme case, let's say you have only one cluster, right? When you have a one cluster, then obviously PCK HTS will be equal to PCKS. But if you have just one cluster, then what will happen? if you have one cluster, then this whole joint distribution will become xi yj HTS, because now there is one cluster where PCK equal to PCK distribution in the smart card data and the HTS data is same, right? Because there is only one cluster, they cannot be different. In that case, this xi yj you can replace with the HTS data, and there is no meaning of CK here. You can get rid of CK. What this data fusion problem will become is P xi yj HTS times P S bar T bar SC. If you have just one cluster, what does that mean? You will be able to maintain the distribution of the x and y in HTS, and you will be able to maintain the distribution of S bar and T bar in the SC data, but whatever you will generate will not be able to maintain the joint distribution of the x, y, s and t that you observe in the HTS data, because that's the main crux. If you look at your first optimization problem, if you have one cluster, it's not just about maintaining the distribution of the xi yj in HTS data and S bar T bar in the smart card data. We also want to maintain this joint distribution that we observe in the HTS data, because if we don't observe that, then maybe we are generating good xi yj's and good S bar T bar, but their joint combination will be absurd. That dependency is only obtained in the HTS data. So the point is, it's a very subtle combination that you have to create in the clusters, where you have enough information transfer, but at the same time, you want to make sure that you maintain the distribution of the xy in the HTS data and S bar T bar in the smart card data. Okay. So when you create the one cluster, you lose the whole jointness, while you maintain the xi yj and S bar T bar distributions the way you want to maintain. And if you have the too many clusters, then you actually end up with again the issue of the zero cell problem, where there's no information transfer happening. Okay, so to learn this from an example, let's try to understand this. Let's go back to our own example that we had in the beginning. So we have HTS data with the 20 observations, smart card data with the 5400, which is like, we are assuming that we are observing the whole population of the smart card, and we are assuming that HTS data has only transit trips right now, because we are not talking about the out of transit trips right now. Okay, so S bar and T bar is same as S and T, and there is no Y here. Like, we are not talking about the trip purpose and the travel modes. We only have the X variable, which is male and female. We have a time variable, which is the departure time, and we have the spatial variable, zone A to zone B, right? And ABC to zone ABC, okay? So it's a little bit simplified version, but let's try to understand what happens. Why do we really need the optimization, okay? So, and what we observe in the SC is actually true distribution, and our objective is to generate the full distribution while maintaining the XY in the HTS and the S and T in the SC distribution and in the SC data, and also going closer to the XY, S and T distribution that we observed in HTS data, because that is important to maintain that dependency that we observed in the HTS data, whatever it is. Okay, so first step, you remember our data fusion equation. If you remove the Y from the equation, what you have XST, XC fuse, and STC SC and PCSC, right? So if you look at this problem, what we do is we create actually total 4 clusters. What do we mean by clusters in this case? The different colors represent the different clusters, okay? So trips going from zone A to B before departing before 9 are in cluster 1. Then green one is going from zone C to ABC is the cluster 2 before 9 a.m. And the departing greater than 9, above 9 p.m., after 9 a.m. is basically cluster 2, cluster 3 in the yellow, and the cluster 4 is the trips coming to zone C after 9 a.m., departing after 9 a.m., okay? So what we are doing here is we are just directly finding the distribution, the joint distribution here. Nothing much is done in this slide using the observations that we have in the HTS data and the SC data. So here we are just finding the joint distributions, basically dividing by the total observations, each cell with the total observations, right? Now the next step is we need to find the XC HTS data, right? Because in the optimization problem also we need to have the XYC. So we don't have Y here. So we need to find the XC HTS, right? So by marginal, so what do? Is we do the marginalization here and we find the, for each cluster, in each cluster we find the probabilities for the males and the females, right? It is differentiated with the male and female and the cluster. So it's the joint distribution of the gender and the cluster in this case, right? So let's say, and we can similarly create the YSTC SC from the, this is just we are directly using the distribution that we generated here. So we have the STC distribution here, and let's say we have XC HTS distribution. Now, to compute this XC fuse, one thing that we explored is maybe we just replace it with the HTS data, right? If we replace it with the HTS data, 0.2, 0.05, 0.2, 0.05, same as what you observe in the HTS data, what will happen is, let's say this is your XST fuse and this is your generated distribution. So if you look at your generated distribution and you compare it with your original distribution, you have 5, 5, 5 for your male and female distributions and the departure time. So you can actually maintain the X and X distribution very well, right? You can have the same distribution that you have in the HTS data for your X if you just use the XST HTS data. But what you don't preserve is S and T distribution. Why? So your initial, the true S and C distribution had 1000, 1800 here, but the distribution of the S and C in the generated data is you have the trips originating from point zone A, zone B, and zone C. This distribution doesn't match with the distribution that we have in the SC data. So if you just use the X and Y, if you just use the XYC distribution from the HTS data, then you end up losing, you cannot maintain the, in the generated data, you cannot maintain the observed distribution in the SC data. Okay, that's the first point that you want to show. Now let's do the optimization. Okay, so this was the XC HTS data, and after optimization, the fuse distribution we got is C1, C2, C3, C4, and this is slightly different than what you have observed in the HTS data. What we do is for each cluster, we find the weight for the male and the female. That's what we mean empirically by solving that optimization problem in this case. In this case, basically for each cluster, we have two decision variables because we have one X only. X has only one variable with the two categories. So we just need to find the, for each of the cluster, how much should be that for the male and the female, right? Once you do that, once you use this fuse distribution here, and STC and C you directly observe from the smart card data, this will be your generated data. And you can see once you use the optimized one, you can actually maintain the joint distribution of the SC data that you observe. This is the observed one, this is the generated distribution. Okay, so to maintain the distributions of the space and time stamps observed in the SC data, we do need the optimization to be solved. Now, the second part, which is even more important, is the clustering part, right? So just to make it clear that when we are solving the optimization problem conditional on the clusters. We are maintaining the smart card constraints, but we make any cluster, we make any type of clusters, we will be able to maintain the smart card data joint distribution. But we don't maintain that how far we are from the X and Y distribution in the HTS data very well. To maintain that, we do that second optimization problem of creating the clusters. Basically, it's not the second problem. We first do this problem and then conditional on the clusters, we solve the P1 problem. But this this P2 problem where we try to maintain the PC HTS equal to PC SC is to really improve the maintenance of the X and Y in the HTS data, or preserve the X and Y from the HTS data in the fused distribution. And the constraint that we put for the non-zero cells, like we want to make sure that when we create the clusters, that these many clusters, not more than 10% of clusters should have the, so let's say you create a cluster in the PC, from the PC data, the SC data, smart card data, then if let's say you create 100 clusters, then at least 95 of them should have observations in the HTS data. So this is kind of a constraint that we had in the, this constraint that I didn't actually go in detail, but we maintain this non-zero cell constraint, which ensures that we don't create too many clusters where you have observations in the SC data, but not in the HTS data, because it is really important to have that, avoid that zero cell problem, and having the joint distribution of the X, Y, S and T very similar to what we have in the, or minimize the distance between the joint fused distribution and in the HTS data. Okay. If you create too many clusters, then you again get into this problem. But you have to create as many clusters as possible when the zero problems, till the point that zero cell problems can be avoided. Okay. So the point of the last part is, you can create the more clusters such that the zero cells are avoided, and we maintain this PC HTS and PC SC, then both things are happening. One is we are going closer to the XY distribution in the HTS data, and we are also going, we are trying to maintain that connection where the information transfer is possible by avoiding the non-zero, avoiding the generation of the zero cells in the HTS data, right? So in this case, for example, instead of 4, we can create the 8 clusters, right? So if we create, you see the different colors are different clusters, and you will see all the 8 clusters have non-zero probability mass in the HTS data. If you look at this one, yeah, it's PC HTS is 0.1, 0.05, 0.05, 0.05, right? So every cluster has non-zero probability mass the way it is created, okay? So this is basically an intuitive way of just saying how you should create the clusters. By the time you can increase the clusters without creating too many zeros, then you are doing fine, basically, right? And what it does is, as I've been telling, it's hard to see here from now, but what exactly it does is, the Y is not here because we don't have Y in this problem. We are going closer to XHTS. We are maintaining our distribution of S and T in smart card data, and we are also trying to maintain the distance, minimum distance with the X, S and T that we observed in the HTS data, okay? Because that's also important to really do the matching between these two data sets, okay? We cannot make it perfect. It's impossible because you're maintaining the STC distribution. So you cannot you cannot make this mapping perfect, but you still want it to be closer to your fused distribution, okay? Okay, let's look at the example, simulation study maybe, and then I'll conclude after the simulation study. So what we do is, we consider the HTS data, okay, actual population. We say that we observe the whole HTS data, we consider that as a population. And in the no data fusion case, we just take the 5% from the HTS sample and we call it as our sample, okay? We call it our HTS sample, this is the data fusion case where what we do is we extract all the transit trips from the HTS data and we call it our SC data. And again, the 5% HTS data, 5% sample as an HTS data, okay? So we define two things. The good thing is now we know the population when we are doing this experiment. So we know how this approach works, right? So if we define two main matrices that are very important. Feasibility, the proportion of the generated observations that exist in the actual population, right? So because we know the actual population, we want to make sure that any combination of X, Y, S, and T, does that belong to the true population or not, okay? So that's basically the feasibility. And the second is proportion of the attribute combination that exist in the actual that are in the actual population that exist in the generated data, right? So what part of the population are we able to present using this method, right? If you use the deterministic method, you will be able to present only few, you will be able to get the 100% feasibility because you are just extrapolating the HTS data, but your diversity will be very low. If you just use a deterministic way of extrapolating your HTS data to the synthetic population, right? So, and with this method, what we will try to do is we will compromise little bit in some situations on feasibility, but we cannot achieve the 100% feasibility the way we are doing the data fusion, but we will increase the diversity significantly, the new attributes that we will generate that present in the actual population. So let's look at some of the results that we observed here. So just to remind, we have the travel mode, 0 walk, 1 is transit, 3 is bike, and 4 is taxi. Trip purpose is 0 is go to work, 1 is work, 2 is home return, 3 is organized hobby, and 4 is entertainment, right? So the first trip, the distributions are very well fit for we are not just showing for the one trip, we are showing first, second, third, and fourth trips on the sequence. The distributions for the trip purpose is pretty well fit with the actual data in the data fusion and the no fusion case, right? So this is good that fusion is not creating some infeasible attribute combinations in that sense, right? If you look at the marginal distributions of the departure time as well as you have the marginal distributions of the departure time for the trip purpose, which is sort of a joint distribution in case of the bivariate settings. That's also, we are doing pretty good in terms of actual data fusion and no fusion. This is just to ensure that this data fusion is not creating unnecessary new distributions that are violating the true distribution. Now let's look at the main results on the feasibility, diversity, and for the no fusion and the data fusion. Okay. So as I said, when you do the no fusion, you just extrapolate the household travel survey data. You have the 100% feasibility, right? Because you are not generating any new attribute combinations. Whatever you are generating is already from the actual population. So you achieve 100% feasibility. When you look at the diversity part, it is very good for commute and the home returns using the SC data, right? Because it captures all of the home return and the other trips. But when you look at the work trips and the organized hobby and entertainment trip purposes, the diversity is pretty bad. Okay. What data fusion does is it can generate those, it can populate those other trip purposes as well, but at the expense of some loss in the feasibility, right? So it generates some combinations of the X, Y, S, and T, where which are not there in the true population, right? Because we are maintaining the XY distributions, we are maintaining the S bar T bar distribution, but we cannot maintain the XY ST distribution jointly as in the population, which is not observed, right? But even maintaining those distribution help you in getting a very good feasibility numbers here, right? Now I think this is more important. So what you see here is you have on the first, on the top is the actual distributions of the trip purpose and the spatial locations. On the middle row is the data fusion one, and the bottom row is the no fusion one, right? So let's first look at the, if you look at the, here, let's look at the first commute, right? In the commute, if you look at the actual distributions as well as the data fusion distributions and the no fusion, not much differences, but darker means more density and yellowish means less density. Okay, so you can see that here in the, in terms of the commute data fusion and the actual, we are able to present these distributions quite well in the generated one with the actual one. But if you look at the no data fusion one, it's the distribution is not as well matched with what you have in the actual distribution, right? If you look at the entertainment distribution, you do have some areas where, like I think these are the business districts in the Seoul, and if you just do the no data fusion, this is what you generate if you just extrapolate your household travel survey data. But this, if you have the, if you do the data fusion, you are able to generate these all other trips, all other trip purposes in the space and time, right? And same goes for the organized hobby and the work. I think I'll just quickly go through the to the actual study. So in the actual study, we use the Seoul data, and we have the only 20,000 attribute combination in the HTS data. But what we generate is actually 337,000 new attribute combinations. What I mean by attribute combination is X, Y, S, and T, the combination of all these three. So if we just use the HTS data, it's very difficult. But we cannot validate in the case study that how many of them are not in the population, because we don't have the true population of the whole activity chains, right? But that's why we did the simulation to see that it works well. But now we are looking for third data sets to validate this, whether the attribute combinations that we are generating are matching with the third data set or not. And we also see some interesting thing that the number of trips per individual that we generated are much higher. And the reason is we have many underreporting trips in the household travel survey data sets, non-commute trips, which we are able to identify in this data fusion. So I think I'll just focus on the main results. So this is the generated one using the data fusion, and this is the HTS, and this is for the work trip, and this is for the entertainment. And you can see that here the more darker arrow, darker dots implies the higher frequency. So we can see that in the business district areas, we do have the more dots, more, I would say, higher frequency of the entertainment trips. They may be the trips after the work, which are difficult to capture in the HTS data. But by combining the smart card data with the HTS data, we are able to find these additional trips after the office hours. And there are other things, but the main point is you are able to generate. The first thing is it's a non-parametric method, right? It can deal with high dimensionality because it was, billions of decision variable problem to we have broke into the I cross J decision variables for the, and solving iteratively for the K clusters, right? And it can handle the, maintain the joint distributions and the marginal distributions wherever we want to maintain. And we are able to get some new spatial patterns in the leisure activities. And it can also handle, because we are first doing the data fusion for the transit trips and then inferring the out of transit trips. So it works well with the incomplete SC trip chains as well. So I think we already know that why we want to understand this joint distributions. This is for non-transport audience. So this is our LinkedIn page if you want to follow more updates. We do have our lab. This was more of an aggregate level, system level work, but our lab also does a lot of work on individual level behavioral science. And maybe I can play this video very quickly and that. This is the eye tracker that we have. That's it. Thank you very much.
All right. Thank you, Prateek. Do you have any questions about his results today? Must have a lot of questions, I think. That's a very informative anyway.
Thank you.
It was a bit of a challenging presentation to give with too many notations, but yeah, please.
Hi, Professor. Thank you so much for bringing us so fancy presentation and quite like the logic chain you think about the data fusion.
Yeah.
So I have one research question about the opinion that you promoted about like this kind of research goal cannot achieve by the generative model. So in order to ask this question, I have separate small question to ask you. So first question is the reason for the clustering is for the dimension reduction, right?
There are two main dimension reduction and finding a common ground where these two data sets can actually transfer information with each other, like handling the spatial resolution conflicts. Right?
Yeah. So as I see from the presentation, like most of the work they are done like directly by setting some parameters at first, and then after the metric calculations.
Yeah.
So my question is, up to this stage, do you think like this kind of process can be replaced by the current existing machine learning based dimension reduction technologies?
We are doing this work separately using the same data set and trying to do that. It's very difficult to maintain the spatiotemporal distributions using even the state-of-the-art machine learning methods. We can maintain the marginal distributions very well, but when it comes to joint distributions of space and time, it's very challenging to handle. So we are still trying to see, we are trying how we can maintain the space and time distributions jointly, but we don't have an answer yet. We are still working on trying some architectures to see if we can maintain. The second thing is like in this method, we can prove things that, okay, if PC is equal to, it's very explainable, right? That in these situations, we can maintain this distribution. In these situations, we cannot maintain this distribution. Or if we are observing some weird phenomena, we can go back to the problem formulation and see, okay, if we change this, that's why this is happening. Okay, why we are, when we replace this fused distribution with the HTS data, why we are not able to maintain the SC data distribution. So I think it's much easier to understand what's really going on in the problem. And actually, this problem, the way we have formulated it, it can be translated to any data fusion problem because it has the data fusion and imputation, two things generally. Some are missing things, but some you need to combine. So you combine and then infer some other things. So it's a very generalizable way, in our opinion. We are trying to make it as robust. So we have spent a lot of time thinking about the clustering, that what are we really achieving? Why can't we use the naive clustering? So we have first version of this paper in TR Part B, and we got a lot of comments from the reviewers, but I think we have addressed all of them. So this is just for us also, it's a journey to understand. We every time do something and we learn something about the problem, and then we prove something, and then we move forward basically. Yeah.
Sure. Thank you so much for the answering. And the second question is like, as you propose on the optimization, like we try to approximate to distribution, like the distribution from the HTS with the distribution from the fusion one, something like that.
Yeah.
And this kind of concept is quite similar with the generative models concept. What do you think of like the possible extension of this work into a generative model, something like that? Because as you mentioned, like it seems like the generative model cannot achieve by that, but still, when you promote with the optimization problem, it reaches similar research questions. Like how can we generate similar distribution of the original?
So the thing is, the issue is the feasibility numbers that you are seeing here, 0.98 and 0.97. With generative model, these numbers drop to 0.6 or 0.7, basically. That's the main issue with the generative models. They create a lot of garbage, and that's very difficult to handle with the generative models.
I see.
So we are thinking how to increase those feasibility numbers, but we are still not sure. But if you really want to maintain the X, Y, and S, or X, Y, and T, remove the S because spatial dimension is very huge. If you want to maintain the X, Y, and T distribution, generative models work very well. As soon as you add the spatial dimension, it's very difficult to maintain the joint distributions.
And the last question is like research field question.
Yeah.
So let's assume that like for this research field, the explainable of the existing method, for example, let's say you say the current method can be explainable well because you can adjust the parameters easily. You can see the differences when you adjust the parameters. And what if, even though like currently, as Professor mentioned, that you try to generate a model, you try some deep learning machine models, and it feels that it doesn't reach well performances. But what if, like, let's say it reached a well performances, but still it has an unavoidable problem that it cannot experience. So what do you think, like, which one is more important in this kind of research field?
Okay, that's
I'm so sorry.
That's more of a trick question. But I would say that being a more analytical researcher, I still prefer these type of formulations. But as you rightly said, that there is a potential in the deep learning and deep generative modeling. So if those models can really explore that, which I doubt they can get such high level of feasibility, but it's possible at some point, right? You might be able to put those constraints in the training process. That's what we are trying to do. Then that automatically becomes explainable, right? If you're putting constraints in the deep learning, then you are automatically making it explainable as well to an extent. So it's like some combination of theory-driven plus the data-driven. I think that can be a solution. That's when we will be achieving these kind of flexibility. So I'm more in the favor of combinations, like how you combine the theory and the data-driven methods together. And that's achievable, I think. That's where we will be able to achieve these feasibility numbers higher than what we have.
Okay, thank you so much.
Very good. More questions? Yeah, Sujit?
Thank you for your nice question. I'm really interested in your seminar. So I have two questions. So you said that the spatial unit of that household data and smart car data is different. So during the matching that spatial unit, is there any possible bias from the different density of bus stops within the drawn or
Yes, so that's a fair point. So there are a few things that we are kind of assuming, right? We are assuming that the X and Y data is better in the HTS, or we want to maintain the S and T distribution from the SC data. But let's say if you have the SC data which is not 100%, but maybe 70%, for example, then in that case we are assuming that the distribution that we are observing in the SC data is same as what we have in the population. But it's possible that what we are observing in the household travel survey data is more closer to the population than the smart card data. So the implicit assumption here is what we are observing in smart card data is more representative of the spatial and temporal locations. What we are observing in the household travel survey data for X and Y is more representative in the STS data. So when you do this, when you expand this data fusion problem to the other settings, then this problem will become very important, that which distribution you are relying more on, or is there any way to get a ground, like is there any way to add more weight to one distribution compared to the other distribution that we learned from. So we have some other formulations going on where we are thinking about the similar problem, that if you have less confidence in one data in the some part of the distribution compared to the others, how do you handle that? And that's a fair point, because it can create a lot of problem. It's not a big problem in this case because it's very clear that smart card data is more representative in the SPAR T-bar, and household travel survey data is more representative in the X and Y. And we still want to maintain that X, Y, and TS distribution in the HTS data, because that's where the linkage will happen between these two data sets.
Thank you for your answer. And next question is, so as you said, the large samples makes the better performance, right? So do you think the minimum number of samples? How do you think the minimum number of samples in that household data?
So this is the question that Land Transport Authority asks us, that how can we reduce the number of household travel survey data collection by using your approach? Yeah, so we can actually try the different number of sample sizes and figure out that at which we can achieve a good feasibility, and the diversity basically will be important. So I don't have an answer, but it can be done using this approach. You try the different samples in a simulation data, and then you can figure out at which stage you are able to obtain a good feasibility and diversity combinations.
And I have extra question. Sorry.
Yeah.
So do you have any plan to use another data set rather than using the smart card data?
Yes. So we are in another paper where we are combining the cell phone, the home and work locations obtained from the cell phone data with the home and work location and the demographics obtained from the HTS data. There we are validating it with the census data, third data. So we are trying to validate the distributions that we are observing through the data fusion. They are more closer to what we are observed in the census data. So entirely new data sets. That's one. In terms of entirely new data, we have some data from the GPS trajectories and the HTS data as well. So we are thinking of how do we infer the demographics from the by combining these two data sets together. So these are the few other things which are going on. The third thing is after giving this talk to Land Transport Authority in Singapore, they are able to give now the household travel survey data and the smart card data to us for Singapore. So we no longer will be using Seoul data, but we are planning to buy the cell phone data for Singapore as well, and then trying to work with all three data sets together actually, and see if not only transit, can we generate the whole activity schedule using this approach by combining all three data sets, because cell phone data will have the tour information for the non-transit trips as well, for the non-transit users.
Thank you.
Yeah, sure.
Thank you for your presentation. Similar to the question regarding merging a lot of data sets, I actually suffer a lot when using the generative AI. I found low diversity. That's what part of the issue.
Yeah.
And if we keep merging, fusioning a lot of data sets, for example, we first predicted XY and then imputed the ST, right? So if that happens consecutively with a lot of data sets, basically we are predicting the data and then using the data to predict another one. Basically, so it kind of feels like circulating, referencing all the data sets.
So it might be a problem if we do that, but in this case, what we are doing is important to just see here that here what is happening is in this strip we are finding the x, y, s bar and t bar, right? So what it gives you is it gives a joint activity schedule only without the space and timestamp of the non-transit activities, and everything else is obtained through the data fusion. And this is good because the next timestamp of the activity as well as the space at a resolution that we are working on is not so difficult to obtain at a distribution level from the HTS data. Because for the non-transit trips, we have no other source except the HTS data. So there is no point of doing more than what you are doing because there is no data, so there is no information that can improve it. The information that can improve has been used at the data fusion step. Then the next part, there is no way that you don't have any information. So you just need to utilize the information that you have. So, but you are right. If we start, not in this approach, but if you start doing the imputation and then you start use that information in another data set. So what we do to address this issue is we try to do the triangulation, right? So what I mean by triangulation is you generate something with one data set, then you validate with the third data set. And you try to have that in your objective functions as well. So for example, in this case, if we are generating S bar, T bar and Y, what we could do is we can validate it with the cell phone data, if we have the cell phone data, because transit trips are very well represented in the cell phone data as well. So this step can be validated with the cell phone data as well. And then you, on top of that, then generate. So you don't generate the different things from the three different data sets. You try to do, if these distributions are observed in the other data set as well, try to use them simultaneously to generate that distribution. You cannot, otherwise it will create a lot of mismatches as you move forward. So the triangulation will become more important if you have more data sets. Yeah, you cannot use the different data sets for different things.
Just one more question.
Yeah.
So I recently worked on a lot to reduce the bias from the samples that I get. Even if we generate, for example, the synthetic population from the single data, and if that data is already biased, and then if you want to try to predict another one, we will need to have to adjust the marginals and joint find some balance where we can have some not biased one. Right?
It can be done.
Yeah.
It can be done in this approach.
Okay.
But cannot be done in your deep generative modeling approach.
I see.
It can be done. Yeah. You can create the weights and incorporate the confidence in each of those data sets and add it here.
That's it. Thank you.
Maybe very last question. One last. Okay, the other guys have been collapsing into finishing. Let's give it a
Thanks very much. Thanks for inviting me.